Welcome to the chapter for Describing the Relation Between Two Variables lecture video. We're going to get into linear regression and scatter plots and things of that sort in this lecture video. The learning objectives for section 4.1, scatter diagrams and correlation. So first let's get into what a scatter diagram looks like. Alright. Two things we should be aware of. The response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. Alright, and so when we graph a scatter plot, the x-axis will be the explanatory variable and the y-axis will be the response variable. We'll look at that. So a scatter diagram, and it's also known as a scatter plot, right? That's the other name that you may hear. It is a graph that shows the relationship between two quantitative variables measured on the same individual. Now sometimes the two quantities can be night and day. They can be very, very vastly different. But what is the same is the commonality is that it is some sort of individual or some sort of a variable that relates them. The explanatory variable is plotted on the horizontal axis, as we said, and the response variable is plotted on the vertical axis. So we now have a problem. Okay, a golf pro wants to investigate the relation between the club head speed of a golf club and the distance that the ball will travel. He realizes other variable besides club head speed determines the distance the ball will travel. Alright, it's not just going to be the club head speed. To eliminate the variability due to these variables, the pro uses a single model of club and ball, one golfer, and a clear 70-degree day with no wind. Okay, so now we have data. The club head speed has been recorded and the distance in yards have been recorded. And now what we do is plot a nice scatter diagram or scatter plot there. Notice we can actually plot this using the Texas Instrument, the TI-84. We would enter the data in a list. We'd have a list 1 for club head, list 2 for distance, and then we would go into the stat plot menu and graph this, and this is what it would look like. Okay, we'll probably demonstrate this later. It appears from the graph that as the club head speed increases, the distance the ball travels increases as well. So to the trained eye that there is some sort of pattern happening, and what we're noticing is that as the club head speed increases, the distances is increasing. Now it's not a perfect increase-decrease, but there is some sort of pattern happening. All right. And quite often you can interchange the different variables in a scatter diagram. It's not always clear which variable will be considered the response variable and which one would be the explanatory in certain circumstances. Okay, so I think our focus is more going to be on the shape and the scatter plot, like the randomness in it, the chaoticness in the scatter plot. That's really going to be our job, trying to interpret what we see. For example, if we happen to see a scatter plot that resembles A, that would be considered linear. Or even if it's going downward as the explanatory variables increase, the response variables decrease, it still gives us a linear pattern. Here's another one, explanatory. We have it goes up and back down. This would be nonlinear. We have another nonlinear. And when we have, this is known as like the cloud pattern. There really is no real correlation happening, no linear sort of pattern happening. So we would say that there's just no relation now. Linear is good, and nonlinear, if it has a pattern, could also be good. We can still model this. All right, but when we're dealing with a cloud type of formation, there's really no relation between these two. Nothing really can be drawn from it, except that nothing can be drawn from it. Okay, so there's the differences there. Two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. And basically, it's whenever the value of one variable increases, the value of the other variable increases as well. This would be called a positive association. And the opposite now. Whenever the value of one variable increases, the value of the other variable decreases. Okay, somewhat like an inverse relationship. Objective 2. Describe the properties of the linear correlation coefficient. So one thing that needs to be said is that when you're creating a scatter plot or a scatter diagram, you don't want to mislead the reader. You need to be very careful about the scales of the axes that you're creating. Alright, so now we're going to get into the Pearson coefficient or the correlation coefficient. It is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and little r represents the sample correlation coefficient. We present only the formula for the sample correlation coefficient. Now, I think the key point here is that r gives you two things. It lets you know the strength, which basically means how straight the scatter diagram is. If the scatter diagram is very, very straight and the lines are in a linear formation, it is going to have a very high strength. And it also gives us the correlation coefficient, also gives us the direction of the linear relation. It lets us know if it's positive or negative. Now, here's the formula. The formula is quite scary. You're subtracting all the data values from the mean of the data values, and you're dividing by the standard deviation, and you do the same for the y. You're multiplying them up and adding them all up, and then you're dividing by n minus 1. The truth is that we will calculate r using technology. We use technology to calculate r. I do not want you to have to calculate the linear correlation coefficient out by hand. But if you did have to, this is what the symbols would mean. There is also another formula. It is even more scarier than the previous. All right, it's a gigantic formula. We will be using technology to calculate r. Now, the thing about r, once it's calculated, you will get a value between -1 and 1. It's inclusive, so r can be -1, and it can also be 1, and everything in between. The closer r is to 1 or -1, the stronger the linear relationship is. The scatter diagram, the scatter plot, the stronger it is. If it's at a +1, this would represent a perfect positive linear relationship. If it's at -1, this would represent a perfect negative relationship. The closer r is to +1, the stronger is the evidence of a positive association, and the closer it is to -1, the stronger is the evidence of a negative association. Now, when you have 0 or anything close to 0, this lets us know we're dealing with more of a cloud type of formation. There's little or no evidence exists of a linear relationship between the two variables. And also, whether or not R is positive or negative. If R is negative, that lets us know we're dealing with a negative correlation. If R is positive, we're dealing with a positive association. That's how you interpret R. This does need to be studied. The linear correlation coefficient is unitless. Okay, it is a unitless measure of association. So the units of X and the units of Y have no role in the units of R. All right. The correlation coefficient is not resistant. All right, so therefore an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient, and that's why they always suggest it's also a good idea to plot the data so we know what it looks like. Here's some examples of scatter diagrams and the R that responds to it, that corresponds to the scatter diagram. Notice that perfect positive, perfect negative, which is very rare, right? It's not practical. You see, look at H. The R is close to 0, but the truth is there is a distinct pattern. And this is why it's important to check. And as far as linear, yeah, no, it's not linear, but it can be. The R is misleading a little because the truth is like, yeah, there could very well be a pattern. It could be a nonlinear pattern. A moderate negative linear relation, roughly negative 0.4, negative 0.5. That's where it's kind of a moderate, where we do see a distinct pattern. So 0.4 and negative 0.4 is where we're starting to get a somewhat stronger type of value. All right. So here we have, it says, suppose that the data are equally dispersed in the 4 quadrants, then the negative products resulting from the data in quadrants 2 and 4 will offset the positive products. The result is a linear correlation coefficient close to 0. All right, now here it says compute and interpret the linear correlation coefficient. That's the R. Again, we definitely use technology, and now I'm going to demonstrate how we use technology at this point. We have a little data set there, and I'm going to clear this out. And I'm going to put my X values in L1, so let me check my data. Let's see. Alright, right now I have 2 things. Let me clear that out. We'll clear this one out as well. And now I'm going to enter in 1, 3, 3, 6, 7, 18, 13, 9, 6, 4. Now, once I have the data in, I can actually calculate the R in several different ways. One way, I guess we'll do it is we'll just go into Stat, and let's go over to Calc, and we're going to choose a linear regression, number 4. and we're going to let our X list be L1 and our Y list L2. And that's all we're going to do. We're not dealing with any frequency distributions. I'm not going to store my equation into a variable to graph it. We're not going to do that. Just hit calculate. And when you hit calculate, you get several things. You actually get the regression line, the equation of the regression line, which we're not talking about just yet. We get the R squared, and then we get the R. Now the R is the one that we seek. Notice I have a negative and very, very strong correlation because it's almost at -1. All right, so we have -0.94. This is good. R squared has a lot of meaning as well. We're not going to talk about that just yet, but it is a percentage. It's the percent of how much the X and Y, the Y is explained by the X. So it's almost 90% of all the Y values are explained by the X value. So we have the data that we're doing are very linked and closely related together. The graph depicts this as well. All right, there's like a one-off. If one of the values were a little bit more linear, man, it'd be exactly linear. All the points can possibly lie on the same line. All right, so we demonstrated how to actually calculate that. Now, if you were to do this up by hand, there's a multiple step process. You first have to calculate the mean, the deviations of all the columns, and then you create these different lists, multiply them out, and then in the end, you're going to divide by n-1. And they got -0.94. It is painstaking. Notice that they're rounding it off to 3 places. All right, this is good. Here's where they say you can use Excel, a spreadsheet, or a graphing calculator, or even advanced statistical, features to create your R, because it is very tedious to calculate out by hand. Looks like here's one way they're able to do it. They have the list, and they use the function CORREL, and they're going the list from A2 down to A9, B2 down to B9, and they get the R. It's 0.939. Determine whether a linear relation exists between two variables. All right. So the first thing we need to do is determine the absolute value of the correlation coefficient, just to see the strength of it. Step 2, find the critical value in Table 2 from the Appendix A for the given sample size. If the absolute value of the correlation coefficient is greater than the critical value, then a linear relation exists between the two variables. Otherwise, no linear relationship exists. Now, if the correlation coefficient is positive and greater than the critical value, then the variable are positively associated. If the correlation coefficient is negative and less than the opposite of the critical value, the variables are negatively associated. So here is our problem, and we had to look up the critical value. So if your data set has 8 values, then your critical value for your R has to be greater than 0.707 in order for there to be a relationship between the two variables. We exceed that by a lot. A significant amount, I would think. So there is clearly a positive linear relationship. Now, we're actually in luck, because the calculator will also give us the it will let us know whether or not there's a relationship. So One way to do this is to go into Stat, go to Tests, and then we're going to go into a linear regression test. We're going to go all the way down. F. Use L1 and L2. Don't have to do anything else. Keep the R's not equal to 0. This is better. Hit Calc. And the P lets us know. The P. So our P, the P is 0.01. That lets us know, because it's small, that lets us know that yes, it is. There is a relationship between them because of our P value. This is a P value. And also our test statistic, the T value, is more negative. So these two values lets us know it has to be less than like 5%. If the P value is less than 5%, then there is a then that means the two variables, the X and Y variables, are clearly related. Sometimes we will even allow it to be related if it's less than 10%. But the rule of thumb is the p-value has to be less than 5%. Now, if the p-value is greater than 10%, like 0.11 or more, then we're just going to reject it. At 10%, we don't go higher than 10%. So the p-value is the one that makes us, we get to make our decision based on that. Okay. And now finally, explain the difference between correlation and causation. All right. Now, just because we say that the two variables are correlated, it doesn't mean that one variable causes the other one to happen. There's other variables at play. All right. All we can say, the most we can say, is that there is a correlation between these variables. We don't know why, we don't know how, but we do know that there is a correlation. And then from there, we can then investigate other factors or even conduct an experiment to justify what's happening, to make sense and learn from our data. And there's something called a lurking variable. Oftentimes a lurking variable is related to both the explanatory variable and the response variable. So we have a certain situation. Here's an example. As air conditioning bills increase, so does the crime rate. All right, so does this mean that folks should turn off their air conditioners so that crime rates decrease? And that's not the case, right? The other lurking variable that we did not account for is the air temperature. As air temperature rise, both air conditioning bills and crime rates rise. That could be the lurking variable right there, is the temperature, the rising temperature. So here's an example of a lurking variable here. And when we plot it, we see that there is actually a somewhat strong negative linear correlation between the two variables. Can we say that colas cause BMD? The greater the cola, the less your BMD. Well, here we have they identified a number of lurking variables that could confound the results, and that is the age of the subjects, the BMI, and their health habits. So that's one thing we got to think about. So 4.2 is the least squares regression section, the least squares regression line. Sometimes we call this the line of best fit. This is the line that we use to make predictions. So when we have a scatter plot that has some sort of linear formation that is strong and we know the direction, we can compose a least squares regression line. And we do need to be able to interpret the slope and the y-intercept of the least squares regression line. And also there's something called compute the sum of squared residuals. Alright, so let's look at an example. Here we do have two different variables, the club head speed and the distance. And if you were to create ordered pairs, we would have 100 to 57, so on and so forth, all the way down. The first part is to find a linear equation that relates club head speed to the distance. And then you're going to graph the line on the scatter plot and then also use the equation to predict the distance a golf ball will travel if the club head speed is 104 miles per hour. The thing about 104 miles per hour is that we don't really have a value for that. Alright? We have values very close to 104. The question is, from this data, can we predict what 104 should be? And we can make a nice, good prediction. First, let's look at the data here. And this is what our scatter plot looks like. So what we're going to do is demonstrate how you would do this using your graphing calculator. Alright, so the first thing we're going to do is enter the data into our calculator. So we're going to go into Edit, and let's clear out the two lists, L1 and L2. And now we begin to enter the values in. Alright, let's continue to enter the values in. Let's go over to list 2. We have 100, 102, 103, 101, 105, 100, 99, 105. Now we're going to go over that. And so now it's just a matter of checking, making sure I didn't make any mistakes. Usually if you make a mistake, it's going to come during the data entry part. So always be very careful with the data entry part. Then we got 257, 264, 277. Just cross-checking everything. It looks good. Everything is matched up. So we've entered the data in. And now let's look at how do we actually graph a scatter plot using our calculator. So what we do is we actually go into the stat plot. Second y equals, we'll pull up the stat plot. We're going to turn on our plot and we're going to select the scatter plot, which is the first type. And when you have that type selected, it's going to ask, they're going to prompt you for the X and Y list, which is correct. Our mark looks good, and now the only thing left to do is to actually plot it. So we go over to Zoom and choose Zoom Stat number 9. Scroll all the way down until you get to Zoom Stat. And there it is. There is our scatter plot. And if we hit trace, we get the coordinates of each one. If we go to second table, well, the table doesn't give it to us, but if we go to graph and then trace, we do get the different values right there from our scatter plot. So that's pretty valuable. It's nice to have that so we can see the different values and things of that sort. All right, we'll use this data later on. Let's keep going. In fact, this is what they did. And now the question is, how do you actually find an equation that represents the linear related data? This is what we call the line of best fit. We're going to learn how to create that. So it's actually a pretty complicated process. Now once we actually have our line of best fit, we are able to make predictions. Now they didn't do a true line of best fit. They just kind of eyeballed it and decided to, hey, let's just create a line through these two, and we have 3 on the upper side and 2 values below and 2 on the line, and this line will be our predictor, so we can use this line to predict values. So they basically took the slope of 2 points and then they formed the y equals mx plus b formula to make an estimation. But we're going to learn how to do it even better. First, let's talk about the residuals. So it turns out residual is nothing more than the observed y minus the predicted y. Graphically, it looks like this. If we have a line and we want to compare the observed value from the predicted value, that difference there, how much it's off by, is a residual. And the thing about it is the least squares regression line is a line that minimizes the sum of the squared errors, or the residuals. This line minimizes the sum of the squared vertical distance between the observed values of the y and those predicted by the line y prime, or y hat. We represent this as minimize the sum of the residuals squared. So it turns out, and it's a very complicated formula, but the least squares regression line is this. So y hat equals b1 x plus b naught, where b1 is the slope, and the slope is the correlation coefficient r, times the standard deviations, the ratios of the standard deviations there, and the y-intercept is the mean of the y values minus the mean of the x values times b1, all right? And that's our y-intercept. So it's actually a huge undertaking to calculate this out. The truth is we never really calculate the least squares regression line by hand. We use technology to do it in this day and age, and that's how we'll do in this class as well. So there is a table here, and oh man, this looks like the table that we had earlier. So I don't have this data in there anymore, but I'll still add it. I'll go to stat and I'll go over to calc or edit, and I'm going to put it in L3 and L4. So I'll just enter the data in here. All right, and now the next thing to do is, how would I find the R, right? And not only that, not only the R of L3 and L4, but the least squares regression line. So we're going to do all of that. So you would go into stat and then calc, and then you'll choose number 4. And I'm going to let it be L3, and the y value will be L4. And this time I'm actually going to store my regression equation and y1. So I'm going to go to my variables list. I'm going to go to the y-vars, functions, and choose y1. So they're going to store the regression equation and y1. So now let's hit calculate. Alright, so it actually calculated that slope and that y-intercept as 18. And then the R is a negative strong correlation of negative 0.94. Now if I hit y equals, it puts the regression line in that equation for me. Actually, wait. Let's try that again. There it is. And if I hit y equals, there it is. And if we were to go to stat plot and turn on a plot, let's go to, yeah, let's go to plot 1. But this time we'll just change the list. We'll make it L3 and L4. It should also plot the line as well. So let's go to zoom and then standard, or zoom stat. And not only did it give us the scatter plot, but it gives us the line of best fit. And this is the line that minimizes the residuals, all right, the squared values of the residuals. And we have to square those residuals because sometimes we'll get a negative residual, sometimes we'll get a positive, but if you square it and you square them all, that will help in terms of creating that. And so this line is the line of best fit. The line of best fit is a unique line, and it is the line that's used to make predictions on the data. And sometimes we can figure out how well it fits and how well of a predictor it really is. There's tests that can be run, but right now we do have a line of best fit, and now we can make predictions for other values that we don't have the data for. Okay. Looks like we got similar things, and now this is how you actually interpret y and y prime, the predicted values and things of that sort. So here's some questions. It says, find the least squares regressions line for the golf data. Draw the line on a scatter plot. Predict the mean, the distance the ball will travel when you hit it at 103. Predict the distance it will travel when you hit the ball with a club speed of 103. And then determine the residual for the predicted value found in part C. So this is what they're going to do. So as you can see, they do utilize this. Now, we actually have the golf data, I believe. Let's take a look and make sure we do have it. I believe we do have it. It's in L1 and L2. So we're going to use those values again. So let's go into Stat, Calc, and we're going to choose 4. This time we're going to let it be L1 and then L2 as well. And let's store the regression line and Y1. Let's store it in Y1. Let's overwrite the last thing we did. And now just hit Calc. Now, this is what I got, and it matches what they have as well. Now, what if you do it and you don't get the R? That basically means you don't have diagnostics on. So you actually would have to go into settings. You would have to go into mode, and you go all the way down where it says stat diagnostics. You have to turn it on. Another way is to pull up the catalog. You go to second catalog at the bottom. This lists all of the functions. It's by alpha, so diagnostics, I can just choose D and then scroll down. I can find the stat diagnostics. I would turn it on. It was already on. And now it will give you the R. So let me know if you're having trouble finding R. You just simply have to turn on your diagnostics. Alright, so now we're able to start to make predictions and answer certain questions. Part A, find the least squares regression line. It has been done. Okay, part B, plot it. So that's what we're going to do next. Let's go back into stat plot. Choose the first one. We're going to make it L1 and L2. Hit zoom 6, no, actually zoom 9 stat plot. That's what we got. Okay, this was used in StatCrunch. We might have to take a look at that later as well. And now we're going to use the line of best fit, or the least squares regression equation, to make a prediction. Because we don't really have the x value, x for 103. So let's try this. We're going to go into Calc, and then we're going to just choose a value for x. We're going to make it 103, and then we're going to hit Enter. And what we get when we do that is 270. And that looks like that's probably what they're going to get as well. Okay, so that did work. And now how to calculate the residual? Well, at this point, you will subtract that predicted value from the real data value. And we get 3.7. And then they say, well, because the residual is a positive number, the predicted value is a little smaller than the actual observed value. All right, so that gives us more information. All right. Let's take a look at interpreting the slope. Again, slopes can be 0, positive, or negative. We don't have a vertical slope. That just doesn't happen. It's undefined. Alright, so the way we interpret the slope from a least squares regression line is we'd say something like this. We'd say, if club head speed increases by 1 mile per hour, because that's how our slope is. This is 3.166 divided by 1. So the distance the golf ball travels increases by 3.166 yards on average. Or we can say, if club head speed increases by 1 mile per hour, the expected distance the golf ball will travel increases by 3.166. Okay, this is how you calculate the residual squared. So from the first example, if you just use the 2 points and you create the slope here, versus the least squares regression line, it looks like the blue line is actually more refined. It represents the data a little bit better. It fits the data a little bit better. It minimizes the number of errors, and it is going to be a better prediction for different values. Diagnostics on the least squares regression line. Here it is. How to compute and interpret the coefficient of determination, perform residual analysis on a regression model, and identify influential observations. Alright, so the coefficient of determination is known as R squared, and it's literally R squared. It measures the proportion of total variation in the response variable that is explained by the least squares regression line. It's actually a pretty deep statement. It says a lot. The coefficient of determination is a number between 0 and 1 inclusive. Alright, so sometimes what we do is convert it into a percentage. If R squared is 1, then that basically means that 100% of the time the line explains variation in the response variable. Now we saw this before, that our predicted line was that blue line, and we calculated the residual between the observed value at 103 and the predicted value at 103. And we realized that there is a change between them. So the difference between the prediction is explained by the linear relationship between the cleft speed and the distance there. So this is just gives you an idea of kind of what the R squared really interprets. All right, let's keep going. So we're literally just squaring R. And the softwares usually will give you this correlation coefficient. Here's an example of what it looks like to have a very high R squared in A. As you can see, that's nearly 100%. And B, the variation is 94.7% of the variability, and Y is explained by the least squares regression line. And then C, as you can see, we have a scatter plot. It is a somewhat positive association between the X and the Y. I wouldn't say that it's a strong or moderately strong kind of linear formation. It's more of a cloud type shape. But the regression line can be calculated. Problem is, the R squared is probably very, very weak. All right, this lets us know that the regression line is not really doing a good job of predicting the Y values. So in our calculator, the R and the R squared are always together. So when we have R, we literally just square it and we can get the R squared. So our second objective is to analyze these residuals. So they actually play a pretty important role in determining the adequacy of the linear model. All right, so we must determine whether the model is appropriate, determine whether the variance of the residuals is constant, and also we must check for outliers. Now, the residual plot can help, and they're plotted in many different ways. Or literally, you're just taking the residuals of each data value and you plot them. As we can see, some of them are negative and some are positive. It's pretty much always going to be like that because the least squares regression line is going to be a line that goes through the middle of all the data values. So you should have approximately the same number of values that are positive and negative. Sometimes you might even have some that are zero. We're right on the line. Alright, as you can see, the linear correlation coefficient is really high. It's 0.99. That's more than the critical value that they said. So we can actually compare the correlation coefficient to the critical value from the table to see if the model is appropriate or not. So there's something called the constant error variance, and the figure illustrates the idea behind the constant error variance. So in figure A, the data appear more spread out about the regression line when x is large. So it's kind of like it's right on in the beginning, but as x gets larger and larger, it looks like the data gets a little more variable. In the residual plot, though, the absolute value of the residues is larger when x is larger and smaller when x is smaller. And this means that the predictions made using the regression equation will be less reliable when x is large because there is more variability in y. Another issue are outliers. Outliers are always issues when you want to make predictions. They're the exceptional case. Usually they're due to error, but there are cases where they're simply exceptional. We can track those outliers in many different ways. There is the box plot of residuals, and it's a modified box plot that calculates the outliers, any outliers. If you're 1.5 times the interquartile range more than the Q3, 75th percentile, then you're an outlier in the positive direction. So there are ways to calculate it. Obviously here we have residuals that are a little bit more than all the others. It's an outlier. An influential observation is an observation that significantly affects the least squares regression line slope and or y-intercept, or the value of the correlation coefficient. Alright, so in this data, they've identified 3 cases where these observations will affect the calculations, our statistical calculations. Alright, so here is some output that the Minitab produced. .4 contingencies, tables, and associations, and we have 3 different learning objectives. Let's get started. So consider the data here represents the employment status and the level of education of U.S. residents 25 years old or older. So as you can see, we have employed, unemployed, and not in the labor force. So this could be thought of as or portrayed as a two-way table or a contingency table. Alright, so we'll look at the marginal distribution of a variable is a frequency of relative frequency distributions of either the row or the column variable in the contingency table. So first it says find the frequency marginal distributions for employment status and level of education from the data in table 9. So we're looking for employment status and the level of education. So that's what we're going to look at, these data values here. And so what we're going to do is calculate the total So here we have the blue entries on the right side represent the marginal distributions of the row variable employment status. And the red is going to represent the levels of education. And so when you compare the different numbers in each column, you'll see that the marginal distribution of level of education shows that there were more Americans with a bachelor's degree or higher than there were Americans who were in high school graduates. All right. Now here it does determine the relative frequency marginal distribution for the levels of education and employment status from this table. So now that you have the totals, what we're now going to do is calculate the marginal values there, the relative frequency marginal distribution values. So we'll go by column, and we can also do it by row. Notice that we're using the grand total of 220,813. And then we're taking the total in this column and the total in this row. And now we have those values. So here it says use the conditional distribution to identify association among categorical data. Alright, so here it says what portion, or proportion we should say, of the following groups of individuals is employed. Those who did not finish high school, then we'll do ones with the high school graduates, those who finished some college, and then those who have at least a bachelor's degree. So for part A, we're getting the 9607 divided by that total. All right, let's now look at some conditional distributions. So it helps to know the formula on how you're calculating these. Notice how we're doing this. So we're listing out all of the different conditional distributions there. We're dividing it by the total of each column there. And it is because we're dealing with the relative frequencies for each employment status. So we're able to create a bar graph there based on the relative frequencies in that chart. It's pretty straightforward. It's another way to think of it. Well, we can quickly look at and see which one varies the most. All right, and in this objective here, we're going to explain Simpson's paradox. It says that the table 13 shows the admissions status and gender of students who applied for the University of California, Berkeley. From the data in table 13, the proportion of accepted applicants is 0.395. So they got that 1748 total divided by all the people who apply. The proportion of accepted men was 0.46 and the proportion of accepted women was about 30%. Again, we're taking the total of the men and the total of the women to see the acceptance rates of each gender. Now, when we add different categories, you'll probably explain a lot more why the discrepancy exists. So it's kind of like lurking variables are being added to the study now. Now we're getting totally different results. All right. So it actually just describes a situation in which an association between two variables inverts or goes away when a third variable is introduced. All right, so that's going to conclude the lecture portion. And what we'll do now is maybe we'll go in and take a look at some practice problems and kind of get a feel for some of the problems that we're going to have on our homework. So that's the next thing we'll do. Alright, so we're going to just pull up the homework and let's just click on some and get a feel for the kind of questions that are being asked and maybe even try a couple of problems in StatCrunch as well. So let's go back into 4.1. Determine whether the scatter plot indicates that a linear relation may exist between the variables. Alright, it's pretty fair. It does look somewhat linear there. Match the linear correlation coefficient to the scatter plot. Well, look at this. This is like perfectly straight and positive. I would put that there. This will not make it negative, a very strong negative, and then somewhat positive, and then this is more of a cloud type. That's what I would do. Yeah, it's pretty straightforward. A lot of matching. Here it says, does this suggest a linear relationship between these exists? Write a sentence that explains. Let's look at the data values there. Okay, so this is just based on, this is how you would use that table that they were referring to. So it says on an international exam, students are asked to respond to a variety of background questions. For the 41 nations that participated in the exam, the correlation between the percentage of items answered in the background questionnaire and the mean score in the exam was 0.833. Does this suggest that there is a linear relation between the student task persistence and achievement score? Write a statement that explains what the results may be. And then it says, does this suggest that there is a linear relation between student tests? So there was a 0.833, but we need to figure out if that's good or not based on our data. And it should definitely be good because our study had 41 nations, but the table only goes up to 30, and it gives you the value. If you exceed this value, then there is a relationship. So I'm going to go with it's greater than the value for 30. So let's check it, and we're good there. It was a good question. Probably need to look at more like those just to see other situations. I mean, that was one where there wasn't that many. Here's our data again, giving us the different critical values. This could be helpful when you want to answer certain questions. Which variable is likely the explanatory variable and which is the response variable? Well, I will say that whenever you're dealing with time as one of the variables, I would say 99% of the time is going to be the explanatory variable. The time will be on the x-axis. So I will pick that the commute time will be explanatory and the response variable's well-being because of this. But let me just double check the other one. The explanatory variable is commute time and the response variable is well-being score because commute time affects the well-being score, or yeah, the commute time affects it because the response variable depends on the commute time. So we'll choose that as the better choice, and we are correct. All right, now if we were to graph the data, we'd have to match it up here. If we open the data in StatCrunch and we were to let's see, we're dealing with regression and a simple linear regression model, and we're going to choose the two different values, and everything else we're just going to leave open. I mean, they're asking for all of these different things. Let's hit it. Well, I I have my R and my R squared. That was really quick and easy to do. That was really nice. And we even have the regression line. They give us the slope and the intercept. So we know it's y equals this. Let's make this a little bigger so we can see this better. For some reason, I'm having a hard time looking at this. Here is the regression line there. So that's like y equals the intercept minus the slope times x. There it is. It's also here as well. They tell us the standard error. And look, the p-value is extremely tiny. That's a good sign. That lets us know that we're dealing with, and even the R. The R is, you know, the absolute value of the R. It's very strong, very close to 1. So we know that there's definitely a linear relationship between between them. And I would actually choose a scatter plot that is a very strong negative linear relationship there. So I'd probably choose D. It's important to make, sometimes like you want to zoom in on it because it's kind of tiny. And then the R was like negative 0.97 or something like that. We found that R and it was pretty accurate. So that's what you would enter in. Let's move on. Yeah. All right. So let's read through this. It says, all right. So we have the data, and then we have the critical values. And what they want to know is which well, first of all, which variable is the explanatory variable? Which one depends on what? It's not obvious which one it is. So we really have to just think about how did they set this up. This is one aspect of the study, was to develop a model that could be used to predict the bear's weight. So if we want to predict the bear's weight, then the weight needs to be the response variable, and therefore the length should be the explanatory variable. Let's check that. We are good. And if we were to graph the data, well, that's one thing we haven't did, and so let's try that. Let's open it up in StatCrunch and try to graph it. Now, if we could graph it easily in Excel, but we have not yet graphed it in StatCrunch, so let's try to do that. All right, and let's look here where it says scatter plot, and we're going to select the length and the width and the weight, and let's zoom out a little bit. It's kind of close there, and hit compute, and there it is. It didn't graph it with the line. We probably had that as an option. We probably could have done that, but there it is. And I guess at this point it'd be a matter of matching the one that we saw with the one that we just created. It looked like A, really. That's kind of what it looked like to me. Oh no, it wasn't. Or maybe D. I didn't really zoom in on it. Oh, C. Oh, C was another one too. Yeah, I just overlooked C. I should have zoomed in on C and looked at it a little closer. The linear correlation coefficient between the weight and the length is basically they want to know what the R is. So we'd have to go back in here into our table. Let's pull up our table and open it back up in StatCrunch. And this time what we're going to do is not graph it, but go to stats and then go over to regression. Do the simple linear regression. Choose the variables. You got to get this part right. Although, wait, it may not actually really matter. The R will probably still be the same. And then, but it will matter for the regression equation. So we did it, and we got our R to be 0.71. Now the question is that R good for the amount of data that we have? We have 12 values in our data. Is 0.719, even if we were to round this to 3 places, it's actually going to be 0.720. So let's type in 0.720, see if it likes that. Okay, that was fine. Now the question is though, is 0.720 significant enough? And we really have to look up the critical value based on our sample size. Now, we do need to know how many is in our data set. How many bears did we have? And according to the data here, we had 12. So 12 is fine. So the critical value for 12 is your R has to be more than 0.576. If your R is more than 0.576, then you are that our data, especially if it's a random sample, right? It's an SRS. If our R is more than 0.576, then that's enough to say that there is a relationship and association between those two variables. So there is a positive, so R is positive. There's a positive association because R is positive. And the absolute value of the correlation coefficient is 0.72. And that's actually greater than the critical value of whatever the critical value was, a 0.576. So that we'll put that down there. And that should be all there is to it. Yep, we got through there. And this is going to be it. Make your way through this assignment. And if you have any specific questions on certain homework problems, reach out, put them in the discussion, or contact me, and I can produce a video that will be helpful and explain the different problems. Until next time.